Mass spectrometry. Let's see how much you remember. You guys had analytical, right? Here's the detector. Right? Here's the detector. And remember, the goal of this detector was to get the fingerprint. Right? Do you remember this? You had some mass, and then you had intensity. And these fingerprints of compounds were mass spectra. Remember doing this? Or remember this kind of talk? Where every molecule known to man, it's just a unique thing in nature, right? These molecules, they always break into the same fragmentation pattern, right? So you have this big molecule, you blow it up, and it breaks into this fragmentation pattern. We call it the mass spectrum. But it's the same every time. So you can have a fingerprint of every different molecule. Cocaine's mass spectrum will be different than ibuprofen, right? So now the goal was this machine, this mass spectrometer, did it. So the goal was this detector had, one single mass had to strike it at a time. Okay. So I was out in the hallway, or somebody was out in the hallway in analytical, remember? And the GC was out here. The GC had to do its job, which was to do what? Well, no, the detector's way over there. That's the mass spectrometer. What was the GC's purpose in this mass spectrometer? Because the mass spectrometer is just a detector. The big thing, it's just a big detector. The purpose of the GC was to separate everything, right? You inject this dude's blood or whatever, you want the pure components to come out. So the GC isn't even, well, it is pictured here, but it's not part of the mass spectrometer. Mass spectrometer is a detector. So the GC, if the mass spectrometer is hooked up to a GC, it can be hooked up to other instruments too, like an HPLC now. But you hook it up to a GC. The purpose of the GC was to do its job. And its job is for pure molecules to be coming out of the end of the column, right? So here they are, right? So these pure molecules, this peak is coming out of the column, okay? Then what? So now the column and the GC are at atmospheric pressure. Look what's going on here with this thing. If the GC does its job, these ions have to go from here all the way over to here. Now that could be upwards of 12 inches or so. So we're talking about ions going in a straight line for about 12 inches. Well, in this room, that's impossible. Why? What's between this hand and this hand? A lot of air. There's no way it's going to happen. It's just like a solid wall. So you have to remove all that air. So this is there's something that's really kind of missing here. And we need some kind of inlet system, because you've got really high pressure and then really low pressure on this side. All right, so, okay. So somehow these pure molecules pass through this inlet system. Okay. Then what was supposed to happen for you to get this fingerprint? What was supposed to happen? They're coming out of the end of this column, somehow passing from high pressure to low pressure, and now, boom! What's the first thing they're supposed to encounter? A flying... I got to do this better when I'm talking about this in analytical. A flying... You got to blow this thing up. How do you blow it up? How do you blow this molecule up? You shoot what at it? Electrons. Okay, now it's not very... Yeah, someone was throwing stuff at it. So I got to get a dart gun or something, right? And then have these molecules fly by. They're never going to hit it, and you hardly ever do. It's a really rare occurrence. So finally one strikes it, right? The thing blows up into pieces. They're flying all over the place, right? So that's the electron impact. So something finally gets struck. Yeah, you can take your detector back, right? Okay, so these pieces are flying all over the place. All right, so this thing, you just, right, throw them in there. All these little pieces. Then these pieces end up going through a mass analyzer. The mass analyzer only lets what through at a time? It does it really fast, though, but only one. What are we trying to get? Trying to get mass. It's only going to let one mass through at a time. And it does it really fast. It scans from like 0 to 1,000 grams per mole in a millisecond or so. But, you know, with computer time, that's a really long time. So it detects, you know, the different masses. Most everything ends up going to the vacuum because it's only detecting one little individual mass at each instant in time. So, but it continually works because remember, there's a lot of molecules coming through this GC. There's a gazillion, billions, trillions, zillions, gazillions of them, right? So we've got room to waste. So it does a pretty good job. In fact, it's easier to saturate than it is to wreck anything. So that's the big picture. Let's go ahead and see if we can answer these questions here. What capability does this detector have that others don't? Brandy, do you remember? We've talked about a lot of detectors. We have flame ionization detector. We've got diode array detectors. We've got photomultiplier tubes. We've got a lot of different detectors. But this guy, no one else can do this. Well, they can kind of pretend, but not near as well. Since every molecule has a fingerprint, it'll take this and just compare it to a library, right? And say 82.6% chance that this is ibuprofen and not cocaine. So let the guy go. Okay, so that's what it can do. It can do these library searches. Give you best guesses of what compounds are. Take it into the jungle and see if you found a new compound or not. Some general concepts behind mass spectrometry. What is a mass spectrum? Well, we kind of sketched one already, right? What were the axes? Yeah, M over Z. Good. What's the M and the Z supposed to stand for? Mass of, well, not mass of the, you can, I would use the word ion or fragment, right? Mass of the fragments, mass of the chunk. Z is, these are ions. Z is the charge. Z is the charge. It's always 1. So there's, but they have it down there just to be. Then what's this axis? Yeah, intensity. Or the number of the fragments, right? The number of them. Like a histogram, really, is what this is. Obtaining a mass spectrum starts with ionization. There's a lot of different types of ionization, Andy. Do you recognize ours? I don't know. You really can't answer that question, Andy, because you haven't done the MS Lab. And the MS Lab forces you to watch this little video from that the manufacturer made, and then they talk about electron impact. They have little videos and things. So you couldn't have answered that. But electron impact. With regard to electron impact, since that's what ours uses, and it's really common, it's probably the cheapest and it works great, least maintenance and all that kind of thing. So the book gives this equation. What do the different terms represent? Oh my goodness. Okay. Andrew, the big M. Now imagine what this is. This is the end of the column. Stuff is shooting into that new really low pressure system. And the first thing that's going on is supposed to be this equation. So big M is probably the sample, the target, right? What you're trying to impact? Well, you're trying to impact these molecules. I think that's why they call it big M. Big M for molecule, maybe, right? But That's your analyte. The GC did its job. So that E minus must be coming from the little, the dart gun or the filament that's shooting out these electrons, right? So that actually strikes. And then you end up forming an ion, and the electron comes flying out, right? It impacted because it doesn't look like a very elastic collision. There's some damage done. What's the little dot mean? What's that little dot? You've seen it in organic. I think you've seen it. I saw it when I took organic. A free radical. Okay. Now, are these supposed to be really reactive, stable things, or what? Yeah, very, very unstable. So they're not going to last very long. Okay. And that's good because we want the thing to fall apart. So this is just a picosecond in time here. Okay. During electron impact ionization, it appears, Brandy, that it's most common to form this guy has cations. And always +1. That's why that Z doesn't really make a whole lot of sense on the x-axis in mass spectra, but that's okay. This should be there, I guess. Electron impact ionization, Melissa, occurs once in, therefore it's, what'd you guess? I kind of gave you some hints. Once in, starts with an M. So therefore it's not. Yeah, not very efficient. Terminology and components of mass spectra. Daughter ions. Alyssa, what would you guess daughter ions are? Well, I look at it really as only one free radical. That's that molecule, right? And then it breaks into its fragments. So they don't like to use the word fragments. They like to use the word daughter ions. I don't know. Maybe it sounds more technical, right? So here's a mass spectrum. They call M to Z 91 being called the base peak. Andy, why would you guess they're calling that one the base peak?
Because it's the biggest?
Yeah, it's the most intense. It really doesn't matter what daughter ion it is. If whichever one is the most intense, they call it the base peak. 106 is referred to as a molecular ion peak. Not all spectra have one, but if you take the mass spectrometer out into the jungle, man, you'd love to find the molecular ion peak. What's the big deal about a molecular ion peak? Anybody?
Yeah, it's all the molecules, the mass of the molecule added up, isn't it?
It's molecular weight. All right, so that's kind of a big deal. If you can find the molecular, it gives a big clue as to what that compound is, molecular weight. So, I mean, it's just one piece of the puzzle. So that's why it's kind of nice to have. You don't have to have it, but you're dealing with an unknown. It makes things easy to rule out if you can have if you know it's molecular weight. And then if we look closely at this, see if anyone remembers this. How is it possible to have a peak with a greater M to Z than the molecular ion peak? Because 106 is supposed to be this compound's molecular weight. But then there's a little dinky peak. Can you see it? There's a little dinky peak right here. It's even heavier. Well, why wasn't that the molecular ion peak? They're saying no. Isotopes. Exactly. What was an isotope again? What was an isotope? Different number of neutrons, right? Different number of neutrons. So it's a little carbon-13, right? Doesn't occur very often, but it's there. So it's gonna. That's why you have a little guy in all this stuff, doing isotopes. And that's just part of the mass spectrum, part of the fragmentation pattern. Some disadvantages of electron impact ionization. High degree of fragmentation. You lose the molecular ion peak. Like we said, that's not good. Then you wouldn't know the molecular weight if you're dealing with something that's not in the library. Molecular weight less than 1,000 grams per mole. Why would that be?
Because then it wouldn't like vaporize.
Yeah, I would say same as the whole idea with the GC. Remember, it has a molecular weight limit, so it has to volatilize. Oh, here's a good question. What intermolecular force are we really referring to? Right? Because you have solid, liquid, gas. And the whole time, they're molecules. So what makes it a solid, what makes it a liquid, is intermolecular forces. Which one are we talking about when we refer to size? That's a good Gen Chem question. We had like 4 different names for the same thing. It was London forces, that's one of them. Van der Waals forces. No, start with the D though. Dispersion forces. Right? So stuff sticks to stuff forces. Really weak, but that size, it becomes substantial. During volatilization, you can get degradation before getting ionized. So these are really kind of the same thing, but not really. I mean, it just because you have to ionize it, it has to be somewhat hot. It may not even be close to 1,000 grams per mole, but it's unstable. Look at sugar. Sugar will caramelize you on you in no time. You're not going to get that through a GC. It's going to be hard. You got to be really careful. General description of instrument components of a mass spec detector. Okay, so the separated analyte. That's occurring in the what again, Andrew?
In the, oh no, column?
In the column, right. Or whatever machine you're hooking up this detector to, right? It's got to be separating these things out. Okay, so where are you going to put these words here? I think the words were all down here. Some boxes might be easier to fill out than others, but we've got 1, 2, 3, 4, 5, 6 words, 6 boxes.
First one's probably the event system.
Yeah. Andrew got his. Brandy? Pick see a box and an answer. Okay, where would you say ion source? Yeah, no, it's the next one. Right, because that right after it enters, it's got to get blasted. Melissa.
Is that the very bottom box? Is that saying like the big box goes straight to the little box?
The blue guy is connected to the dashed line which surrounds the entire detector.
That'd be the computer readout.
Wouldn't be computer readout be that last box over there?
Yeah, well, this one will make sense to be the computer readout because where it's coming from is the detector. Yeah. Okay, Mal, you're still.
The vacuum system is the third box.
Right here? Yeah, I would indicate vacuum system as the blue guy. You see, it's 10 to the minus 5 to 10 to the minus 8 torr. What's a torr? What's a torr? It's another unit. It's a unit of pressure. So it's the same as a millimeter of mercury. I don't know if you need to know that, but the point is 10 to the minus 5, 10 to the minus 8, really small numbers with a pressure unit. So, and then the whole thing is in this dashed line, and the blue is connected to it. So it's trying to say, or I'm trying to say, that That's the vacuum system, keeping everything at that really low pressure. And then it makes sense then, I think, that you got the flow diagram, the GC or whatever, the column, like Andrew's, well, how do you spell column? The column does its job, right? And then the inlet system somehow gets it to go from a atmospheric pressure to really low pressure. It gets blasted in the ion source. All these fragments have to go through a mass analyzer, which picks one mass at a time. The mass that does get through hits the detector. The detector is scanning this in an order of a millisecond or two. Okay. It makes these histograms of intensity and mass to charge. Okay, we kind of did that in analytical. Did you want to do that again?
It's been a long time since
Yeah? Could, when we started, could you visualize it or not? Because we can go through it. It doesn't take that long. All right? Want to try it?
Is it what we did back there?
Okay, hang on. I need a quadrupole. What did I use as the quad? You guys remember any of it? What did I use as the quadrupole? Somebody at least remembered?
She just took it.
Okay, so I need help. Man, he's already gotten up.
I do this one last time.
He did remember something then. All right, I need my quadrupole people. All right. Well, we're gonna have to figure this out. It'll work. We got enough. Come on. I need one person over here. Brandy, come over here. Yeah. And then Mel or somebody hold that one. Okay, and then here's the bottom. We don't need anyone to hold the bottom one, I don't think, right? You just got to hold the top one over here. And then we needed you to throw crap at Andy.
Nice. I like this job.
And then what's, oh!
She's the one that gets hit.
No! She's got to be what's the one piece that's missing? Can you see what's happening here? The GC's doing its job, right? So he's going to come through the door pure molecules. He's going to be trying to impact them with electrons, missing almost all the time, right? You have to, there's one piece that's missing in the flow diagram. None of this is going to work. Oh, we actually have two things that are missing. We need a vacuum and we need you said a detector, right? Okay, so find me the detector. All right. So everything has to get, all the air has to get sucked out of here. Right? It's coming in. Okay, so let's say you got hit. Say you got blasted, right? So the pieces go flying everywhere. Okay. So how did this work? Do you remember?
He like threw the one specific
So now he's, how did these different fragments get through here? What did these bars doing?
Is it like their lecture, the positive and negative?
Positive and negative sign. There might even be some magnetic forces going on in here. Why? Because he's got a charge and he has to get through here. So if these have the right combination, they can actually get that charge to move here if it weighs that certain mass. So they're applying an energy to it. So if you bounce with the right energy, right? If you bounce it, try again. If you bounce with the right energy, you can get it through there, right? Okay, now use that same energy to bounce this guy through. I mean, you won't even get it hardly there, right? But you see what I mean?
Yeah.
Because with gravity and thing, it's kind of screwing it up. But the point is it might be better to do it this way, to do the bouncing thing, right? You just barely let this guy go, and he'll bounce through. Because you got to get him to be in the middle here somewhere. If I want to get that golf ball to bounce, right? I got to really push it pretty hard to get it to go through. So if you apply golf ball energy, this thing goes, where does it end up? In the vacuum. Right? So only one mass will get through at a time. Now you remember?
Yeah.
Okay. All my little fragments. My daughter ions are everywhere.
Where's the ping pong ball go?
I think it was flying over here somewhere. Okay. I think we got them all. So to wrap up, mass spectroscopy, a tick. What did tick stand for? Man, they like these abbreviations and this stuff, don't they? What's a tick? Because when you guys haven't done the MS yet, right? When you do the MS, geez, they're going to look exactly the same as what detector? What was the other detector? You have used this detector on the GC. The FID. You did GC FID. What was FID? Flame ionization detector. And you got these chromatograms, right? This was time and signal. A tick looks exactly the same. It looks exactly the same. A tick does.
That's like the chromatogram.
It's a chromatogram. It looks just like a FID chromatogram. But there's got to be something different about it. TIC is the hint. Total ion. Not. Well, that'd be a chromatogram. Count doesn't sound bad though. Yeah, it does. Total ion chromatogram. That's TIC. So what you have to do, and you're going to do this, I think, in the very first GC lab. What you're going to do is you really got to zoom up on this. Really, you're going to pick any peak, and you're really going to zoom up on it. So if you really zoom up on it, you start seeing, let's say this is what you zoom up on. You start seeing this kind of thing. See where it's kind of jagged? So what you're, all it's doing is just connecting the dots. So at each, depending on what frequency that, remember this whole mass spectrometer is scanning so many times per second. So if you slow it down, you can actually start seeing the dots. And what it's doing is all of the intensities, well, let's put it this way. You put that little cursor on here, it's going to go to one dot or the other, right? Put your cursor on there and right-click on it. What comes up? The mass spectrum. So that dot is essentially just that at that time, and the y-axis is the addition of all the intensities. That's all it is. So there's a lot of information in a tick because every single dot, and you hardly see, and they look smooth. There's a lot of dots. I mean, there's a lot of mass spectra here. It consists of mass spectra, the added intensities of all those daughter ions. And you don't see the mass spectrum until I think it's double right-click on it. And then a new window pops up, and you see the mass spectrum that gave rise to that point. So that's why they call it a total ion chromatogram. It looks just like a regular chromatogram, except it really consists of mass spectra. So these files are huge. Every single data point is a whole nother spectrum. So the idea here is you usually want to, and we're not going to really have time to get into this, you want to pick the peak, and then that's where you double right click, and then you get the mass spectrum, right? And then you do a library search off of that. Otherwise, you're biasing the high mass of the low mass. So we'll talk, we really don't have time to talk about that. But it kind of makes sense just to pick the peak anyway, right? So you get the mass spectrum at the peak of your tick, and then that's what you do the library search on. Does that make sense, Andy? Did I lose you?
Yeah. So you do library search on the signal? Or?
Yeah, so you do a library, you can only do library searches on the fingerprint, and the fingerprint has to be a mass spectrum. Well, where are the mass spectra? You don't even see it. I mean, it looks like a regular chromatogram. So where are the mass spectra? Well, if you add up all of the heights, you would get one number. And add up all those heights, that's what this axis is. So right here, that's all the heights added up for that mass spectrum. So you can't do a library search on this kind of thing. You have to do it on the mass spectrum. Okay. Okay. To identify an unknown analyte peak in a tick, a mass spectral library search is performed. Okay, so, right? Can you imagine that? You have all these different mass spectra of all these compounds, and someone just saved them all, right? Someone just ran all this stuff, National Institutes of Standards, or someone more really trustworthy, right? And then they're selling these great big libraries, so we don't have to run them all. We just buy the library, and we did. We bought one. We bought a library. Okay, so you do a research project, and you get a really nice match. A perfect match in a library search is not a guarantee. What's the best and perhaps only way to verify the identity of an unknown using a mass spectrometer detector? So you're in court. And you're getting paid big bucks to run this machine, and you get to go to court once in a while. And we just got a graduate student who's, oh God, she hasn't told me. She applied for this forensic science lab job, and that would be part of her job going to court. Anyway, she gets pulled into court, and if the lawyer kind of knows what's going on, how are they going to know? That's why lawyers in chemistry, big bucks. Your arguments can be extremely strong in the environment in a lot of situations. But the point is they could say, hey, how did you do this analysis? I mean, yeah, it's a nice library search, but that's not good. I mean, you don't know. What do they mean? You don't know. All that match, that's 98.99% match, all it matches is some guys who did an analysis with a certain compound, and the fingerprint seems to match with his machine, but you have a different machine. You have you have your own columns. You have your own. They've been used different amounts of time. There's so many different things. You can't say, oh, it's not a direct comparison. I mean, it gives you a clue, but it's not exact. You can't base someone's life on that. I mean, I would bet money, but I wouldn't bet someone's life on it. So what's the only way to verify, sitting in court, saying, oh yeah, that guy had Tic Tacs in his pocket and not cocaine? What's the only way to verify a compound?
Run, like, just a pure sample of...
Run the pure sample on your machine. Exactly. That's what you have to do. But it's kind of nice because the library search told you what pure compound to run. So you kind of saved you a huge step, right? So, but you got to run that pure compound. Exactly. You got to go out and buy it and run it.
Well, what if it's like cocaine?
Those forensic science labs have to have access to all that stuff.
Yeah.
They have to. Otherwise, you can't verify your analyses.
You gotta be able to buy all these.
So.